Hello everyone. In our today's video, we'll be trying to take a very important topic, which is chemical periodicity, which help us to understand the various other chemical properties and physical properties of the elements, the compounds. Okay. In this particular video, we'll be trying to understand the variation of many physical properties, which decides the chemical nature of a particular substance. Okay. This properties are atomic radius, ionization enthalpy, diagonal relationship. We'll be trying to take in a very short way, just trying to focus on how they are varying and what is the reason of the variations. So let us start with our video on chemical periodicity. So the first thing which you can see in your screen is the periodic table. I hope all of us have seen this periodic table. And if you see it properly, what you can find out is that there are 18 groups in the periodic table. Okay, and there are 7 periods in this particular modern periodic table, as we say. This is also known as Bohr table. Okay, and remember that the basis of this particular periodic table is its atomic number. Okay, this periodic table is based on modern periodic law, which states that the periodic function or the physical and the chemical properties are periodic function of their atomic number. That means if the atoms or the elements are arranged in increasing order of their atomic number, then after a regular interval, a period, okay, after a certain interval, similar properties will reoccur again. Okay, this particular periodic table is based on electronic configuration of elements. Okay, and if you see any group in this particular periodic table, what you will find out is that in any group, the particular element which you are taking, and if you compare with the rest of the element, their electronic configuration, particularly the outer electronic configuration, which decides the valency of a particular element, is always same. And since the valency is same and since the configuration is same, that's why the properties tends to repeat. And that is what we call as chemical periodicity. Apart from that, when you see the number of periods, we have 7 periods. And remember that these periods are very specific. They have a number, and these numbers are not just random numbers. These numbers are as a principal quantum number. What is this principal quantum number? This principal quantum number tells us the number of shells in that particular atom in that period. That means one particular period will always have the same number of shells. If I take period 3, that means the number of shell in period 3 elements will be 3. If I take period 5, the number of shells in period 5 element will be 5. Okay. Our periodic table is classified into 4 categories. You can clearly see S block, P block, D block, and F block. The left-hand side block is known as the F block, S block. The middle is the D block. The right-hand side is the P block, and the lowermost block is the F block. How we have classified them is based on, again, on electronic configuration. It is on the basis that when we write the electronic configuration of the element, into which subcell the last electron goes. Okay, if the last electron goes to the S subshell, we call it S block element. If the last electron goes to P subshell, we call it P block element. If the last electron goes to D subshell, we call it D block element. And if the last electron goes to F subshell, we call it F block element. So that is how actually the classification is done. Okay, so let us try to go for the chemical periodicity, and let us try to see that how the properties varies in this particular periodic table. Okay, so the repetition of similar electronic configuration after a definite period is the cause of periodicity of the properties of element. As I have mentioned that the periodicity is, or the cause of periodicity is because of the repetition of the similar electronic configuration, okay, which actually repeats after a definite interval. And those definite interval is nothing but it is after 2 element, then it's after 8, then 8, then 18, then 18, then 32, and the 32 element. So that is nothing but the number of electron present in different shells. Okay, that is basically the electronic configuration again. The chemical properties of the elements are dependent on the valency electron. That's what I have told you. Okay, so the chemical property basically depends on how many electron a system can give, how many electron a system can take, or how many electron a system can share. Depending upon that, only the chemical properties are decided. How a substance will form, whether it will form oxide, what will be the oxidation state it will be showing. So all these things, all the various chemical and the physical property which we really deal with basically depends on valency. Okay, and what was found out is that the variation in electronic configuration leads to the variation in properties. After a definite interval, as I've told you, those intervals, reoccurrence of the similar electronic arrangement takes place when the number of valency electron is the same. Okay, in every group, if you see, the number of valency electron remains the same. As a result, there will be a regular gradation or repetition of the properties of the element. That is what we call as chemical periodicity. And the properties which are directly proportional or related to that electronic configuration, what will happen is we'll show a regular gradation when we move from left to right in a periodic table, or when we move from top to bottom. Okay, that is, or these properties are nothing but known as periodic properties. And that is what we are trying to understand today. So let us try to take one by one of periodic properties and learn their variation in group and in period. Okay, so the first periodic property which I am taking is atomic and ionic radius. All of us knows what is atomic and ionic radius is. Okay, so basically we are trying to talk about the size of an atom or an ion. So what we are basically trying to understand in this particular topic is how does the size varies in the periodic table when we move from left to right across a period or down the group. So let us try to take that variation across a period. It was found out whether it is atomic radii or ionic radii, both will decrease when you move from left to right across a period. You take any period, no matter whether it is the first or the last period, whenever you move from left to right, generally it should decrease. The basic question is why? Why atomic or ionic radius should decrease? So the reason for that is when you move from left to right, as already mentioned, that it is actually the arrangement of the element is basically based on their atomic number, increasing atomic number. Atomic number is nothing but number of protons in the nucleus. So when what will happen is if this atomic number goes on increasing when we move from left to right, then the nuclear charge also increases. When this nuclear charge increases, then the electron will be actually pulled closer to the nucleus. And very important thing, when we move from left to right, as I have already mentioned, when we are moving in a period, the number of shell remains fixed. The principal quantum number remains same. As a result, there will be no increase in the number of shell. So the electron will be at a finite or at a fixed distance from the nucleus. And because of the increased nuclear charge, what will happen is it will be pulled closer to the nucleus because of the force of attraction. As a result, the size will shrink, it will decrease. Thus, the opposite case, when we move down the group, the atomic or an ionic radii will increase, the size will increase. Now, why? Because when we are moving down the group, we are moving from one period to another. When we are moving from one period to another, we are increasing the number of, or we are increasing the number of shells, or the principal quantum number is increasing. When the number of shell is increasing, obviously the nucleus and the electron goes far away from one another. And through our basic concept of electrostatic, what we know is that as the distance between the two opposite charges will decrease or increase, okay, then the atomic radii will also increase and decrease. So over here it is increasing, so our electrostatic force will decrease. So as a result, the nucleus cannot hold the electron. As a result, the electron cloud expands and it results into increase in atomic or ionic radius. So that is how we can understand that how it varies. Now coming for the next topic in atomic and ionic radii is the size of cation and anion. So basically we are trying to discuss now the ionic sizes, okay, or the ionic radii. Always remember that if a system converts to anion, its size will always increase. Means if an atom converts to anion, means gain one electron. That is how a system converts to an anion, right? It gains electron. If it gains electron, its size will increase. Now the question is why size will increase? Since the nuclear charge remains the same, always remember that. Like if a chlorine converts into chloride, the atomic number is remaining same only. Proton never gets changed in a chemical process. Always remember that. The number of proton always remains same. Okay. Number of proton never increases or decreases in a chemical reaction or when there is increase in positive or negative charge in a system. What happens or why a system is getting positive or negative charge is basically because of the transfer of electrons, not protons. So nuclear charge remains the same even if it converts to an ion. Like if I have chlorine, a chlorine has an atomic number of 17. So a chloride, Cl minus, will also have an atomic number of 17. But the only difference is chlorine has 17 electron, chloride will have 18 electrons. So what will happen? That additional electron creates a repulsive force or repulsion in the system, which will enlarge the domain of the electron cloud. It will enlarge, it will expand the electron cloud. As a result, the size will increase. Okay, there will be repulsion in the system. Taking the another case of cation, a cation, whenever it is formed from a parent ion, remember that the size will always decrease. Now the question is again, why the size is decreasing? Now, again, the same concept. When I convert any atom to cation, the nuclear charge remains the same. But electrons are going out of the system. When electrons are going out, then there will be less electronic repulsion, and the effective nuclear charge in the system is increasing. As a result of which, what will happen is the electron cloud will be pulled closer to the nucleus. As a result, size will decrease. So always remember that anions will always be bigger than the parent atom, and cation will always be smaller than its parent atom. Very, very important. Okay. Coming for a similar topic in atomic and ionic radii, which is isoelectronic species. So what is this isoelectronic species? It can be any species. It can be atom or a cation or an ion which have the same number of electron. Iso means same or constant, and electron means, or electronic comes from electron. So isoelectron, having the same number of electrons. Okay, so different species but having the same number of electron, and since they are different species, obviously they'll have different nuclear charges, different number of different atomic number, different number of protons. So different number of protons but having the same number of electrons are isoelectronic. And in such cases, a very, very important point to note down is that in such cases the size decrease with increase in atomic number. Okay, always remember that whenever you have isoelectronic species, their size will decrease when atomic number of that species will increase. Like if I have these 4 cases, you can see potassium ion, argon atom, calcium ion, and chloride ion. If you have this 4 ion, if you see the atomic number of potassium is 19, atomic number of argon is 18, atomic number of calcium is 20, and atomic number of chlorine is 17. The number of proton is different, so nuclear charge is different. But see the number of electron. Number of electron in potassium is 19. It has lost 1, so it becomes 18. Number of electron in argon is 18. Number of electron in calcium is 20. It has lost 2 electron, becomes 18. Number of electron in chlorine is 17. It has gained 1 electron. It has become 18. So all of them have 18 electrons. So when they have 18 electrons, that means they are isoelectronic, all of them. But can you see this has 19 proton, 18 proton, 20 proton, 17 proton. When you have difference of the number of proton, obviously the pull of the electron cloud will be different. So the one which will have the highest number of proton, that means the highest atomic number, will pull the electron cloud toward itself with maximum force. So its size will be the smallest. So if I write the order, the decrease in the order, so chloride will be the biggest because it has the smallest number of smallest atomic number, 17. So it cannot pull 18 electron toward itself as much as argon, then calcium, and finally, potassium, and then finally calcium. Calcium has 20 number of protons and 18 electrons. So it can pull the electron cloud much or more efficiently than the other. So that is how we can understand the variation of size in isoelectronic species. Very, very important. Okay. Now coming for the next topic, that is ionization energy. So how do we explain ionization energy? How do we understand ionization energy? If I go with the exact definition of ionization energy, it is the energy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state. So in very simple word, it is the energy required to remove the last electron from a system, from an isolated gaseous atom. Okay. Now the question is, when or for which atom it will be more and for which atom it will be less. Now, a simple thing to understand over here is ionization energy depends upon atomic radius. Now, if atomic radius is smaller or less, what will happen? The nucleus and the last electron will be close, attractive force will be more, so it will be difficult to take it out. If atomic radius is bigger or larger, then what will happen is the nucleus and the outer electron will be far, the forces of attraction will be weak. When the forces of attraction will be weak, it will be easier to. So the point to note is that when size will increase, when radius will increase, ionization energy will decrease. When radius will decrease, ionization energy will increase. So they are inversely proportional to one another. And that is on the basis of what which we'll be discussing. So variation across a period, it will increase. Now, why it will increase? Just now what we have learned, what happens to atomic radius? Atomic radius decreases. So when atomic radius will decrease, nucleus and the outer electron will be very close. It will be holded very tightly. When it will be holded very tightly, what will happen? Obviously, it will be very difficult to take out the electron. So you have to expend more energy to take it out. And that energy is nothing but ionization energy. So as you move from left to right, ionization energy goes on increasing and increasing and increasing. Okay, so that is what is mentioned in the reason. Variation down the group, just the opposite case. When you move down the group, size will go on increasing because the principal quantum number is increasing. The shell is going on adding one by one. So as a result, what will happen? The nucleus and the outermost electron will be very far. When it will be very far, electrostatic force of attraction will be weak. So the electron, to remove it, will become very, very easy. So as a result of which, the ionization energy will decrease. Okay, so important to note that is ionization increases from left to right and decreases down the group. And the reasons are mentioned. Electron gain enthalpy. How to define electron gain enthalpy first? Remember that electron gain enthalpy is energy released. Ionization energy is the energy absorbed by the system. When it absorbed, it releases actually the electron if the energy is sufficient. But electron gain enthalpy is the energy release when an extra electron is added to a neutral gaseous atom. So if I take an atom and add an electron to it to convert into an ion, okay, so what will happen is the system releases energy in the process. The energy which is released is nothing but electron gain enthalpy. Now try to understand that if a system after taking that electron becomes more stable, it will release more energy. Whenever we say stability, stability refers to lower energy state. So to lower its energy, it releases that energy. That energy which is released is known as electron gain enthalpy. That's why in most of the cases in electron gain enthalpy, we add this word negative electron gain enthalpy. So when we say negative electron gain enthalpy, it means that the energy is released. When we say more negative electron gain enthalpy, it means more energy is released. Okay, so that is how the negative word over there is taken. Okay, it is basically for the release of energy, exothermic process. Okay, now the question is when the release of energy will be more, when the system will become more stable. So when the system will be more stable, when it can hold that extra electron, when it can hold that extra electron, when the nucleus is close to that extra electron where it can pull it. That means when size is small, the incoming electron will be pulled by the nucleus easily, so it will become stable. When size is big, the incoming electron will be far away from the nucleus, so it cannot pull it. So size, actually the electron gain enthalpy will become less, or the system will become less stable. So let us try to see the variation. So variation across a period, it will increase across a period. See, when we move from left to right, it increases. Now what is the reason? Again, the reason comes to the size only. When you move from left to right, the size will decrease and nuclear charge will increase. So nuclear charge will pull the incoming electron toward itself, make it stable. As a result, there will be more release of the energy as electron gain enthalpy. Just the opposite case again, variation down the group. When we move down the group, electron gain enthalpy decreases. When it decreases, now why it decreases? Because the size is increasing. When size is increasing, it is going away from the nucleus, the incoming electron. When it is going away, obviously it cannot be pulled, it will not be stable, it will not be releasing more energy, but it will be releasing less. So electron gain enthalpy decreases. So that is how we can understand the variation. Okay, the variation is very much similar. The reason and the variation is very much similar with ionization energy. Coming for electronegativity. Now remember that whenever we talk about electron gain enthalpy or electron affinity, okay, in some of the textbook it is mentioned as electron affinity also, the electron gain enthalpy. Electron gain enthalpy and electron affinity are same thing. Most of the students get confused with electron affinity and electronegativity. Electron affinity is electron gain enthalpy. What is electronegativity? It is not energy involved. It is basically a tendency, or you can say a power of a particular atom in a bonded state to attract the shared pair of electron toward itself. The more power it has, or the more tendency to pull the shared pair of electron in a bond toward itself, we call it more electronegative element. Okay, so it's just a tendency, not energy involved. Okay, how does it vary? Again, it decreases when you move, increases when you move from left to right. Why it increases? Again, the reason is very same. It's because of the size. Okay, because when you move from left to right, size will decrease and there will be increase in nuclear charge. Both of this will result into more pull of that shared pair of electron toward itself. It will pull more because nucleus is very close, attractive force will be more, size is small, it will be pulling it more powerfully, nuclear charge is more, it will be pulling it more powerfully. So obviously the electronegativity will go on increasing whenever you move from left to right. And whenever you move down the group, just the opposite case, it will decrease. And the reason is also the same. It is again due to increase in atomic size. So when you move down the group, obviously size will increase. So the shared pair of electron will go far. When the shared pair of electron will go far, what will happen? Obviously, it will lead to the increase in the size and the attractive force will decrease. When attractive force will decrease, so what will happen is the electronegativity will decrease. Okay, so that is how we can understand. Now coming for our next topic, that is diagonal relationship. Now this is an interesting phenomenon which happens, okay, which was found out between the second group and the third group element. Okay, it was found out that certain elements of the second group and third group element show similarity, okay, which are present diagonally to one another, okay, diagonally in the periodic table. They are neither present in the same group, they are neither present in the same period. They are present in different group, in different period, but if you see their position in the periodic table, they are diagonally present, okay, and such relationship are known as diagonal relationship. So if I'll take group 1 to group 1, group 2, group 13 and group 14, okay, second period element, lithium, beryllium, boron and carbon. And if I take the third period element, magnesium, aluminum, sodium, magnesium, aluminum and silicon, it was found out that lithium and magnesium has similar property, beryllium and aluminum has similar properties, boron and silicon has similar properties. See, they are neither present in the same group, neither in the same period. Then also they show similar properties. This particular relationship between a pair of elements in the second and the third period, neither belonging to the same group nor in the same period, but diagonally related, or they are present diagonally in the periodic table, such relationship are known as diagonal relationship. Now the question is why it happens. The reason for it was found out to be of its identical ionic radii. The ionic radii of these elements are nearly same, and because of which the other property which are related to radii tends to become same, and their polarizing power, that is charge to size ratio, is very much similar. Because of this, what will happen is their properties, chemical properties, physical properties tends to remain very, very similar. Okay, so that is what we call as diagonal relationship. Okay, coming for the next. Now this is also a very interesting thing which happens in our periodic table, which is the anomalous properties of the first element of the group. The first element of any group, okay, which you can take from group 1 to group 18, particularly group 1, 2, and group 13 to 18, that is S block and P block. The first element, if you see the second period, okay, when we say the first group, that is the second period, okay, of the periodic table, this element tend to show some properties which are very much different from the rest of the member of its group. Okay, it should not happen. When we say a group is nothing but those elements which show similar properties, but they tend to show some properties which is very much different, anomalous properties. What is the reason behind it? It was found out there are a few reasons which result into this anomalous property. The first one is small size. Since they are the first element of the group, obviously they will have the smallest size. Because of the smallest size, they will have large charge to radius ratio. Compared to the other, they will have very, very large. Third, they'll have very high electronegativity. Just now what we have seen, because size will decide electronegativity. Very small size, very high electronegativity. Very high ionization enthalpy. Again, the same thing. Size is very small, high ionization energy. And very important, they have non-availability of d orbital for bonding. Remember that we are talking about second period element, principal quantum number 2. So for principal quantum number 2, for second shell, we do not have d subshell. We have S and P subshell. As a result of which, because of this unavailability of vacant d orbital in the system, in the atoms, they cannot expand their valency, they cannot expand their octet, and as a result, other elements of this group can do that. Okay, as a result, they will show many anomalous property, which actually is not shown by the other members of the group. Okay, so very, very important for understanding the anomalous property. These are the 5 reasons which is leading to this anomalous properties. Okay, now finally, if I try to summarize it, okay, so this is very important now. So we have done 4 properties: atomic radii, ionization enthalpy, electron gain enthalpy, and electronegativity. Always remember that if you see over here, variation across a period, it decreases. Variation down a group, it increases. Wherever it is decreasing, all the rest 3 are increasing. And wherever it is increasing, all rest 3 are decreasing. That's what is very important, because ionization enthalpy, electron gain enthalpy, and electronegativity is inversely proportional to atomic radii. Okay, so always remember that if atomic radii will increase, the rest 3 property will decrease. If atomic radius will decrease, the rest 3 property will increase. Now, these are the general variations, how it should vary, but it was found out that there are some exceptions, okay, which are happening, okay, where it is not going in the way how we expect it to. They are not varying in the same way. Okay, some of them I have taken in this particular video. So let me just explain to you. I have taken 3 variations, which are very important, which are very common. Okay, the ionization energy of beryllium is more than that of boron. Okay, if you see your position of beryllium and boron, okay, beryllium is towards the right and boron is towards the left. We are moving from left to right. Okay, beryllium is group 2, boron is group 13. So when you are moving from left to right, ionization enthalpy should increase, but beryllium has more and boron is less. That means it's decreasing. Why? Because of fully filled configuration of beryllium. Beryllium has a 2s2, outermost fully filled configuration. And always remember that if the configuration is fully filled or exactly half filled, it tends to remain more stable. Okay, it tends to retain that particular state. So it will not be so easy to remove that electron from that particular state, because it makes the system stable. Okay, which we can understand with the help of symmetrical distribution of electron and the exchange energy. Okay, and coming for nitrogen again, nitrogen is in group 15 and oxygen is in group 16. When you move from group 15 to 16, you are moving from left to right. When you move from left to right, you should expect that the value will increase. But again, the same thing, nitrogen has higher value, oxygen has lower value. It is decreasing. Why? Again, if you write the configuration of nitrogen, the outer shell configuration of nitrogen is 2s2 2p3. 1s2 2s2 2p3, atomic number 7. If you can see p3, p orbital can take a maximum of 6. So it is p3, it is exactly half filled, and which becomes very stable. As a result, it does not prefer to lose energy. Okay, so if you compare with oxygen, oxygen will be readily losing electron, because oxygen configuration will be 2s2 2p4. If it will lose one electron, it will be very easily converting into a very stable state. So oxygen will prefer to lose electron. Okay, while nitrogen will not prefer because it will lose its stability. And the third exception which I have taken is for electron gain enthalpy of fluorine and chlorine. What we have learned is electron gain enthalpy decreases when we move from top to bottom. If you take group 17, fluorine, chlorine, bromine, iodine, when you move from fluorine to chlorine, you are moving down the group. So fluorine should have more electron gain enthalpy than chlorine, but it is opposite. Chlorine has more electron gain enthalpy and the highest electron gain enthalpy, and fluorine has less than that. Now, why it is happening? It should not happen. It was found out it is because of very small size of fluorine. Fluorine has a compact second shell. Try to understand. It has only 2 shells, and in the second shell, it has 7 electrons. If you bring an extra electron, that is what electron gain enthalpy means. You have to bring an extra electron. After taking that electron, it will release energy. So in the process of bringing that electron, what will happen is that the system becomes very actually repulsive. Okay, the 7 electron will repel that incoming electron very, very powerfully, as a result of which it will reduce the attractive force from the nucleus, resulting into less stability of that system compared to chlorine, which has 3 shells. Okay, and in the third shell is comparatively very, very bigger compared to the second shell, and it can easily fit in the electron. As a result, if an electron comes into chlorine, it tends to become more stable than when an electron actually is taken by fluorine. That does not mean fluorine cannot take electron. A very wrong concept goes over there. It does not mean fluorine cannot take electron and chlorine can take. We are just saying that chlorine has more tendency to take electron than fluorine. That is measured with the help of electron gain enthalpy. So that is how we can understand this basics of chemical periodicity, which becomes very, very important to actually go for or to understand the chemical properties and the physical properties of various substances, various elements. Okay, so that is all about this particular video. So thank you everyone to subscribe this channel for explanation on various topics in chemistry.